Module 3, Lecture B, Functional API. By the end of this lecture, you will be able to define Keras models using the Functional API with explicit input and output tensors. Implement models with branching or skip connections using the Functional API graph structure. And visualize and debug functional models to ensure correct tensor shapes and connections. Functional model inputs, outputs, using Keras input. When building models in a functional style, you first define an explicit input object that represents the incoming data. This object is not real data, but a symbolic placeholder that specifies things like dimensions and batch size. All layers in the model connect back to this input, so the framework can track how tensors flow and what the intermediate sizes are. This approach gives you a clear picture of what the network expects, especially when the architecture is more complex than a simple stack of layers. It is important to define input representations explicitly so models can handle different data types correctly. For images, this might mean fixed-size color images with 3 channels. For text, it might be sequences of word indices with varying lengths. And for tabular data, it might be feature vectors. Each input object specifies the structure of a single example, while the framework automatically manages the batch dimension. This clear definition helps avoid shape mismatches and ensures that layers such as convolutional and dense layers can be combined smoothly. Defining an explicit input object for your model anchors the computational graph and makes it easier to inspect, visualize, and debug. Each layer then processes tensors derived from this input, so you can clearly trace how data flows through the network. This clarity helps you see how changes in input shape affect the model's behavior. It is also valuable in collaborative work because it creates a shared, concrete understanding of what the model expects as input. Python code using Keras input. This script introduces how to use functional inputs in Keras with a focus on the Keras input object. It is designed to show the basic idea of defining inputs in a functional style rather than a simple sequential model. You are expected to run the cells in order so you can follow the explanation step by step. By the end, you should understand how functional inputs are set up and used within a Keras model. TensorFlow is already installed in Google Colab, so you can use it there without any extra setup. If you run the same code outside of Colab, you may need to install TensorFlow yourself. The commented instruction in the material shows how to install version 2.20 using the Python package manager pip. This helps ensure you have the correct TensorFlow version so the code runs smoothly. We start by importing TensorFlow, a main library used for machine learning and deep learning. From its Keras interface, we bring in the Layers module to access different types of neural network layers. We also import the Model class, which lets us build models using the functional style. With this setup, we can flexibly define and modify neural network architectures. We use TensorFlow's random module to set a fixed random seed so that any operations involving randomness give the same results every time the code runs. This makes our experiments reproducible, which is important when we are debugging. It also allows us to fairly compare model performance across different runs since the random factors stay consistent. This line checks and prints the version of TensorFlow currently in use. It helps you confirm that your environment is set up correctly and matches what the rest of the code expects. Knowing the exact version is important because different versions can change features or syntax, which may affect how your code runs. We specify the size and format of each image the model will receive by setting its height and width to 28 pixels and using a single channel. This configuration matches small grayscale images, such as those in the MNIST dataset. By defining these values, we clearly describe the shape of the input data that the model expects to process. We define an input tensor in Keras that is tailored for grayscale images using a shape that matches our data, 28 by 28 pixels with one channel. This definition tells the neural network exactly what kind of input to expect, so it can correctly interpret the data as images of that size. By explicitly setting this input shape, we ensure that Keras manages the structure of the data properly as it flows through all the layers of the model. We print the shape of the input tensor to confirm that it has the expected dimensions. This check ensures that the input layer of the model is correctly set up to receive the data. In this case, we verify that each input is a grayscale image that is 28 pixels high, 28 pixels wide, and has a single channel. Confirming this shape helps prevent configuration errors before training or inference. We begin by applying a two-dimensional convolutional layer to the input images, using 8 filters with small 3x3 kernels. This layer uses the ReLU activation function to introduce nonlinearity into the model. Together, these choices allow the network to extract important features and learn spatial patterns in the images more effectively. This line applies a max pooling operation to the output of the previous layer to downsample the feature maps. Using a pool size of 2x2, it reduces the height and width of the input feature map by half, keeping only the maximum value from each small region. This lowers the computational cost and helps control overfitting, while also adding some translation invariance to the learned features. After the convolutional and pooling layers have extracted features, we flatten their multidimensional feature maps into a single one-dimensional vector. This step is essential because the dense or fully connected layers that follow require a one-dimensional input. By converting the feature maps into this flat vector, we allow the model to connect all features and perform more complex transformations. This prepares the network to make final decisions in the later layers. We now add a dense or fully connected layer to the model with 16 units, so it produces a vector of 16 outputs. This layer uses the ReLU activation function to introduce nonlinearity, which helps the model learn more complex patterns. It takes the flattened output from the previous layer and transforms it into a new representation that the model can use in later stages of learning. We finish the model by adding a dense output layer with 10 units and a softmax activation function. Softmax is used here because it produces probabilities across multiple classes. Each of the 10 units represents one possible class, so the layer outputs a probability distribution over all 10 classes. This layer takes the output of the previous layer and completes the model's architecture for multi-class classification. To build a functional model in Keras, we call the model constructor with two main arguments: the input tensor that defines the shape of the data, and the final output layer that produces the predictions. This connects the input data through all the intermediate layers to the output. We can also assign a name, such as simple functional model, to help identify it later, especially when working with several models. Once this step is done, the neural network architecture is finalized and ready to be compiled and trained. The code calls a summary function on the model to get a concise overview of its architecture, including the layers, their output shapes, and the number of parameters. Nested layers are not expanded in this view, keeping the summary compact. It also shows which layers are trainable. This summary is used to quickly verify that the model's structure is correct before starting training or evaluation. We use TensorFlow's random uniform function to create a small batch of dummy image data, generating 4 images with a chosen height, width, and number of channels. This synthetic data has the same shape as the model's expected input. By doing this, we can test how the model behaves and verify that it runs correctly without needing any real image data. We check that our dummy batch of image data has the same shape as the model's expected input, ignoring the batch size in both cases. By comparing these shapes, we can detect any mismatch between the data and the model's input requirements. If a mismatch is found, an error is raised to alert us to the problem. This verification step is important to ensure the data is correctly formatted and to avoid runtime errors when the model runs. This code runs a forward pass through the model using a batch of dummy images, meaning it feeds the input data through all the layers to produce predictions. Setting training to false puts the model in inference mode, so it does not update its weights or use dropout, which are only applied during training. This step is used to see how the current version of the model performs on new, unseen data by examining the output predictions it generates. We begin by printing the shape of a small dummy batch of image data to confirm that its dimensions match the input shape defined for the model. Then we print the shape of the model's predictions for this batch. This prediction shape should show 10 outputs, one for each class the model is designed to recognize. Checking these shapes verifies that both the input data and the model's output are correctly structured for later analysis or evaluation. We print the first prediction vector to see how the model represents its output for a single example in our dummy batch. Converting this prediction to a numerical array lets us easily inspect the values. These values show the model's confidence levels for each of the 10 possible output classes, helping us understand what it thinks is most likely for that sample. This script shows how to build and test a simple neural network using the Keras Functional API. It defines an input for 28 by 28 pixel grayscale images, then applies a convolutional layer with 8 filters, max pooling to reduce the spatial size, and a flattening step. A dense layer with 16 units further processes the features, and a final dense layer with 10 units and softmax activation produces class probabilities for classification. The model is compiled and summarized to reveal its architecture and trainable parameters. A dummy batch of 4 images is passed through the network to generate prediction vectors of length 10. And the script prints the shapes of the inputs and outputs, along with the first prediction to illustrate the model's behavior. Multiple model outputs. In functional neural network design, a model can be built to produce several outputs at the same time. You feed input tensors through shared layers, then branch into different final layers that each generate a specific output. This structure forms a directed graph where each branch focuses on a different prediction, such as classifying a car type, estimating speed, or giving a confidence score. During training, these outputs share the early computations but are treated as separate predictions to be learned. When one input can support several related tasks, it is often useful to design the model with multiple outputs. For example, a single medical image can be used to predict disease presence, severity, segmentation, and risk. And a single user and item pair can be used to predict click probability, watch time, and purchase likelihood. By defining multiple output tensors, the model learns these tasks jointly, sharing information in the early layers while allowing later layers to specialize. This multi-output setup improves data efficiency and generalization by capturing features that are useful across related objectives. When a model produces multiple output tensors, each one needs its own target data and loss function, such as one for classification and another for regression. During training, these separate losses are combined, often with chosen weights, so the model can balance performance across all outputs. This setup lets a single system handle several tasks at once, like predicting driver drowsiness and gaze direction together, or generating both sentiment and topic labels from one text. By clearly defining each output tensor and its role, you keep control over how the network learns and how the tasks share information. Python code, multiple model outputs. This material demonstrates how to use the Keras Functional API to build a model with multiple outputs that share the same base layers. It constructs a very small example network where several outputs are produced from a common core. The model is trained briefly, and then the script reports the shapes of the outputs and shows sample predictions. Overall, it serves as a simple illustration of shared layers and multiple outputs in Keras. The line starting with an exclamation mark is a shell command, not Python code, and it is used to install TensorFlow version 2.20.0 to match the rest of the script. Different TensorFlow versions can behave differently, so using this specific version helps ensure compatibility. Because the line is commented out, it will not run unless you remove the comment marker. It mainly serves as a reminder to install the correct TensorFlow version before running the script. We begin by importing 3 key tools for our script. The operating system module lets us interact with the system, for example, to work with files or environment settings. The random module provides functions for generating random numbers, which we can use to create or control random data. Finally, we import NumPy, a numerical computing library that makes it efficient to handle arrays and perform mathematical operations. Together, these imports prepare the environment for data manipulation and randomization tasks in the script. We start by importing TensorFlow, a library used to build and train machine learning models. From TensorFlow, we then import Keras, which offers a simpler, high-level way to create neural networks. Finally, we bring in the layer components from Keras, so we can define different types of neural network layers, such as dense layers, that will form the structure of our model. We set seed values to make our results reproducible, meaning we get the same random numbers every time we run the code. First, we fix the seed for Python's built-in random functions. Then we do the same for the random number generator in NumPy. We also set the seed for TensorFlow's random number generator so that operations like initializing neural network weights are consistent across runs. By using the same seed value in all 3 places, we ensure that every part of the code that relies on randomness behaves predictably and repeatably. This line displays the TensorFlow version used in the script. Knowing the exact version helps you check compatibility and understand which features are available. This is important because TensorFlow updates can introduce major changes that affect how your code runs. The code first checks whether any physical GPUs are available using TensorFlow's device listing tools. If at least one GPU is found, it sets the device type to GPU so the model can run its computations there. If no GPUs are detected, it falls back to using the CPU instead. This logic ensures the model automatically uses the most efficient hardware available for training and inference. The code checks whether a physical graphics processing unit is available and then prints which type of device will be used for computations. If a graphics processor is found, it selects that. Otherwise, it falls back to the central processor. This message helps you understand the hardware environment in which the model will run, which can influence both performance and compatibility. We define 3 key parameters for our model. The input dimension is 8, meaning each data sample has 8 features. We use 64 samples in total, which are the data points for training and testing. Finally, we set the number of classes to 3, so the model predicts one of 3 possible output categories. Together, these choices shape the input data and determine how the model's output layer is structured. We use a random number generator from a numerical library to create input data for our model. This produces an array with the desired number of samples and input dimensions. We explicitly set the data type to 32-bit floating point values so it is compatible with TensorFlow. Using this format helps TensorFlow perform computations more efficiently. This code uses a random integer generator from a numerical library to create classification labels for a dataset. Each label is a random integer that represents a class, and the total number of labels matches the number of samples. The labels are chosen from 0 up to 1 less than the total number of classes. This approach is useful for simulating classification tasks where every sample must be assigned to one of several possible categories. To create regression targets, we generate continuous random numbers using a numerical library and arrange them in a two-dimensional array, with each row representing one sample and a single column for the target value. We then convert these values to the float32 data type so they are compatible with TensorFlow operations. This gives us properly formatted continuous targets for training a regression model. The code converts integer class labels into a one-hot encoded format using Keras tools. In multi-class classification, each class is represented as a binary vector whose length equals the number of classes. Exactly one position in this vector is set to 1 to identify the class, and all other positions are 0. This representation is important because it matches the expected input format for the categorical cross-entropy loss used when training classification models. Before building the model, the code checks the shapes of the input and target data to make sure everything is correctly structured. It first prints the shape of the input array, confirming the number of samples and input dimensions. Then it prints the shape of the classification targets, which are one-hot encoded, to verify they match the expected format. Finally, it prints the shape of the regression targets, which are continuous values, to ensure they are suitable for the regression task. These shape checks are important for debugging and confirming the data is ready for training. In a Keras functional model, we begin by defining an input tensor that represents the features the model will process. Its shape is set using the input dimension, which specifies how many features each sample contains. We also assign it a clear name, so it is easy to reference later. This input definition serves as the entry point for data and provides the foundation on which all subsequent layers are built. We begin by creating a small shared dense layer with 16 units that uses the ReLU activation function to process the input tensor. Pause. This layer, called the shared dense layer, converts the raw input features into a more abstract representation. That shared representation is then used by both the classification head and the regression head of the model. Pause. By sharing this layer, the model can learn common patterns that are useful for both tasks. We now add a second dense layer to the shared part of the model, called Shared Dense 2. This layer has 8 units and uses the ReLU activation function. Its role is to further process the features produced by the previous layer, so the model can capture more complex patterns in the input data. By stacking this additional layer, we increase the model's ability to learn richer representations. We define the classification output layer as a dense layer that takes the shared features from the previous layers and produces the final predictions. This layer has 1 unit for each class, so it can output a probability for every possible class. It uses the softmax activation function, which converts the raw scores into probabilities that sum to 1, making it suitable for multi-class classification. We also assign this layer the name class output, so it can be easily referenced later in the model configuration. We create the regression output head using a dense layer from Keras with a single unit, so it produces 1 continuous value suitable for regression. The activation is linear, which means the model can output any real number without applying a nonlinear transformation. We name this layer regOutput to clearly indicate that it is responsible for the regression prediction. This layer is connected to the shared feature representations from the previous dense layers, allowing the model to use those learned features to make its final regression output. We are building a Keras functional model that produces two outputs from the same shared layers. We first define the model inputs using the features we prepared earlier. From the shared representation, we then create one output for classification and another for regression. Finally, we name this combined structure the multi-output model, which lets us solve multiple tasks efficiently with a single shared network. The code first prints a controlled summary of the model using a custom function that suppresses the usual detailed output, which helps keep the display concise. It then prints the names of the model's output layers so you can confirm that the architecture is configured as intended. In this case, those outputs correspond to the classification and regression heads, allowing you to verify that both parts of the model are present and correctly set up. The model is now being compiled, meaning it is set up for training with specific choices for optimization, loss functions, and metrics. It uses the Atom optimizer, which is efficient and adaptable. For the classification output, it applies categorical cross-entropy loss and tracks accuracy to see how often predictions match the true labels. For the regression output, it uses mean squared error as the loss and mean absolute error as the metric to measure the average size of prediction errors. This configuration lets the model train and evaluate the classification and regression tasks separately and effectively. The model is trained using a fit procedure that takes input data along with targets for both classification and regression provided together in a dictionary. Training runs for 3 full passes over the dataset, known as epochs. During each pass, the model processes the data in batches of 16 samples before updating its weights. The training is configured to run silently, without printing progress information to the console. The code evaluates the model to measure how well both the classification and regression outputs perform. It calls the model's evaluation function with the input data and the corresponding targets for each output. The classification targets are provided in one hot encoded form, while the regression targets are continuous values. Detailed logging is turned off to keep the output concise. This evaluation step computes the loss and any metrics defined during compilation, allowing you to verify the model's performance on the given data. This code prints a compact summary of how well the trained model performed. It reports evaluation results for both the classification and regression tasks in a single place. The stored results contain the key performance metrics for each output, and printing them makes it easy to quickly review the model's overall effectiveness after training. We begin by selecting a small batch of data, in this case the first 2 samples from the dataset, to test the model on a simple subset. We then call the model's prediction function to generate outputs for these inputs. The model produces 2 types of predictions at once, one for the classification task and one for the regression task. To keep the output focused only on these prediction results, we turn off detailed logging by setting the verbosity level to 0. The code prints the shapes of the model's 2 prediction outputs to check they are structured correctly. It first shows the shape of the classification predictions, which tells you how the predicted class probabilities are arranged for each input sample. It then shows the shape of the regression predictions, indicating how the predicted continuous values are organized for each sample. Together, these shapes help confirm that the model is producing outputs in the expected format. This code displays the model's predictions for the first data sample from both its classification and regression outputs. It first prints the class probabilities, which indicate how likely the sample is to belong to each possible class. It then prints the regression prediction for the same sample, which is a single continuous value. Together, these outputs show both the model's discrete class predictions and its continuous estimate for that sample. This script shows how to build and train a Keras functional model with two outputs, one for classification and one for regression. It sets a fixed random seed for reproducibility, checks for a GPU, and then creates shared dense layers that feed into separate output layers. The classification head uses a softmax activation, while the regression head uses a linear activation. The model is compiled with categorical cross-entropy for the classification loss, mean squared error for the regression loss, and it tracks accuracy and mean absolute error as metrics. After training for a few epochs, the script evaluates the model, prints the results, and runs predictions on a small batch to illustrate the shapes and example values of both outputs, demonstrating how to handle multiple tasks in a single neural network. Constructing Keras models. When building a model with the functional approach, think about how data flows from inputs through a series of transformations to outputs. Treat the input as a placeholder for real data, such as an image or numerical features, and imagine it passing through layers that extract patterns or combine features. This flow can be viewed as a directed graph, where each layer is a node and each connection shows how data moves. You then implement the model by explicitly connecting these layers, forming a concrete graph with clearly defined inputs and outputs for prediction and training. To build a model that predicts house prices, you first define an input that matches your data, such as a vector of numerical features like location, size, and age. This input is then passed through several layers, where each dense layer transforms and combines the features to learn useful patterns. The output of one layer becomes the input to the next, forming a chain from the initial input tensor to the final prediction tensor. By clearly connecting the starting input to the final output, the model has a well-defined path for how data enters, is processed, and produces the predicted price. Explicitly constructing models is powerful because it works consistently across both simple and complex architectures. You define how data enters the network with input tensors, pass it through a sequence of layer transformations, and then specify output tensors for predictions or key results. This creates a clear, inspectable structure that is easier to understand, modify, and extend. That clarity is especially important for collaboration, since it lets team members follow the model's logic without digging through complex or hidden definitions. Python code, constructing Keras models. This script introduces the basics of the Keras Functional API, emphasizing how to define models with explicit inputs and outputs. It is designed to be run step by step in a Google Colab environment. By following the cells in order, you can see how functional models are constructed and connected in a clear, structured way. TensorFlow is already set up in this environment, but if you run the code elsewhere, you may need to install TensorFlow version 2.20.0. Using this specific version is important to ensure compatibility and proper functionality. This is especially crucial when building and running Keras models, which depend on the correct TensorFlow version. We start by importing TensorFlow, a powerful library used for machine learning and deep learning. From TensorFlow, we use the Keras module, which offers a high-level way to build and train models. We also bring in the layers tools from Keras, so we can define the different parts of our neural network. This setup provides the basic components needed to design and manage the structure of our model efficiently. We set a fixed random seed in TensorFlow so that our code produces the same results every time it runs. By choosing a specific seed value, such as 7, we ensure that all random operations behave consistently across runs. This determinism is important for debugging because it lets us reliably reproduce issues. It is also essential for reproducibility in machine learning experiments, allowing others to confirm and build on our results. This line checks and prints the version of TensorFlow that is currently in use. It provides a quick way to confirm that your environment is using the expected version. This is important because the rest of your code may rely on specific TensorFlow features or behaviors that can change between versions. We begin by deciding how many features each input sample will have, and in this case, we choose 4. This means every data point is represented by 4 numerical values. Setting this number is important because it determines the shape of the input layer in the neural network. The input layer must be configured to accept exactly these 4 features so it aligns correctly with the data. We use the Keras input function to create an input tensor for our model, and we set its shape to match the 4 features in our data. We also assign it a clear name, such as house features, to indicate what kind of data it holds. This step defines the input layer of the neural network and establishes how data will enter and flow through the model. We add a dense or fully connected layer to the model with 8 neurons, so it produces 8 output values for each input. This layer uses the rectified linear unit activation function, which introduces nonlinearity and helps the model learn more complex patterns. We give the layer a specific name for easier identification later. The input to this layer is the previously defined tensor that represents the features of the house. We now add a second dense layer to the model, which takes the previous layer's output as its input. This layer has 4 units, so it produces 4 values for each input sample. It uses the ReLU activation function, which keeps positive values and sets negative values to 0, adding nonlinearity. Named Dense2 for clarity, this layer further mixes and transforms the features so the model can learn more complex patterns. In this step, we add the final dense layer of the neural network, which produces a single output value representing the predicted price. This layer uses a linear activation function, so its output is just a weighted sum of its inputs. A linear activation is suitable here because we are solving a regression problem and need to predict a continuous value. We name this layer price output to clearly indicate its purpose in the model. In the Keras Functional API, we build a model by explicitly specifying its input tensor and output tensor, then passing them to the model creation function. This defines how data flows through the network from the input layer to the output layer. We can also assign a name, such as price model, to help identify it later, which is useful when working with multiple models. This approach makes it easier to design and manage complex architectures by clearly mapping how information moves through the layers. Calling the model's summary function produces a concise overview of the model's architecture, listing each layer, its output shape, and the number of parameters. With nested layers not expanded, it keeps the display compact while still showing which layers are trainable. This summary helps you quickly confirm that the model is built as intended and is a useful tool for debugging its structure. We begin by importing the numerical computing library in Python called NumPy, which helps us perform mathematical operations efficiently. Then we set the number of samples to 6, creating a small dataset for our work. This choice determines the size of the feature matrix and the target values we will build, ensuring they have the correct dimensions for training and testing the model. We first generate a one-dimensional array of floating point numbers using a numerical range function with a total length equal to the number of samples times the number of features. We then reshape this array into a two-dimensional matrix so that each row represents a sample and each column represents a feature. This reshaping step organizes the data into the correct structure for the model and ensures it matches the input shape expected by the neural network. We generate the target values using a function that creates evenly spaced numbers, starting at 100,000 and ending at 160,000. The number of samples controls how many target values are produced. We set the data type to 32-bit floating point so it matches the format of our feature data. This gives us a simple linear sequence of targets that the model will learn to predict. Before training a model, we need to make sure our feature and target data have compatible shapes. We check that the feature data is arranged as the number of samples by the number of features, so each sample has the correct set of inputs. We also confirm that the target data has one value per sample. These checks help catch shape mismatches early and prevent errors during model training. We now compile the model, which means we prepare it for training by defining how it will learn from data. We choose the Atom optimizer because it is efficient for large datasets and complex models. For the loss function, we use mean squared error, which measures the average squared difference between predicted and actual values and is well suited for regression problems. We also track mean absolute error as an additional metric, which looks at the average absolute difference between predictions and targets to give another view of prediction accuracy. The model is trained using the fit method, which takes the input features and target values and learns from them. It runs for 5 epochs, meaning it goes through the entire dataset 5 times. The batch size is 2, so the model updates its weights after every 2 samples. The training output is set to be silent, so no progress logs are printed during this process. Next, we use the trained model to make predictions from the same set of input features. We pass the feature data into the model, which processes it and produces estimated output values. The prediction function is called with the feature matrix as input, and logging is turned off so no extra messages appear during this step. In effect, we are applying the fitted model to the data to estimate the target values, which here are the predicted prices. We first check the shape of the input features to confirm their dimensions and make sure the data going into the model is structured correctly. Then we check the shape of the model's predictions to verify that the output dimensions match what we expect. Together, these checks confirm that both the inputs and outputs have the correct format and that the model is producing results in the intended structure. We now print a few example predictions alongside their true target values to quickly check how well the model is doing. Using a simple loop, we go through the first 3 samples, or fewer if the dataset is smaller. For each sample, we display its index, the actual target value, and the value predicted by the model. Comparing these side by side gives an immediate intuitive sense of the model's performance before doing more detailed evaluation. This script shows how to build a simple neural network with the Keras Functional API to predict a single value from 4 numeric features. It sets a fixed random seed for reproducibility, defines an input layer, 2 hidden layers with ReLU activation, and a final linear output layer. Then it compiles the model with the Atom optimizer and mean squared error loss. A small dummy dataset with 6 samples and corresponding target values is created, and the model is trained briefly for 5 epochs with a small batch size. After training, the script uses the model to predict outputs for the same inputs, prints the input and output shapes to verify dimensions, and compares a few predicted values with the true targets to illustrate how the model performs. Functional graph connections. Calling layers in Functional API. In functional model building, each layer is treated as a function that transforms input tensors into output tensors, and chaining these calls creates a computational graph. Instead of a simple fixed stack of layers, this graph structure lets you build complex architectures with branches and merges. You can route tensors along different paths, combine different types of data, or process multiple streams in parallel. Each time you call a layer, you add nodes and connections to this graph, enabling more flexible and sophisticated model designs. Calling layers on tensors lets you clearly track how data shapes and meanings change as they move through a network. Each layer takes an input tensor, transforms it, and passes on a new tensor, so you can follow these changes step by step. This process builds a directed graph that records both tensor shapes and how layers are connected. Such a structure is especially important in complex workflows like medical systems, where different types of data are processed along separate paths and then merged for a final prediction. In functional model building, you apply layers directly to tensors, which lets you create more complex connection patterns than a simple stack of layers. The same layer can be reused on different tensors to share weights, which is useful when you need to compare items like documents or images. A layer's output can feed into several other layers, creating a fan-out pattern, and multiple tensor inputs can be merged in fan-in patterns. These flexible connections allow you to design architectures that match specific tasks, such as combining data from different sources or integrating different types of information. Python code, calling layers in Functional API. This material introduces the basics of the Keras Functional API, showing how layers are called and combined like functions on tensors. It explains how to connect layers in a flexible way rather than in a simple sequence. Finally, it demonstrates how to build a small model that includes branching paths and skip connections to illustrate these ideas in practice. This part of the script explains that if TensorFlow is not already installed in your environment, you should install TensorFlow version 2.20.0. Doing so makes sure you have the exact version the script was written for. This helps prevent compatibility issues and ensures the code runs as intended. We begin by importing TensorFlow, a powerful library for building and training machine learning models. This import also brings in the Keras tools, which offer a high-level way to construct neural networks. With TensorFlow available, we can define layers, compile models, and carry out training and evaluation in a unified and efficient workflow. This line checks and prints the version of TensorFlow currently in use. It helps you quickly confirm that your environment has the correct TensorFlow version installed. This is important for compatibility and to make sure your code runs as expected. By reading the version information, you can verify that the setup matches the requirements of your project. We set the random seed using TensorFlow's random module so that any operations involving randomness give the same results every time the code runs. This makes our experiments reproducible, meaning we can repeat them and get consistent outcomes. It also helps us debug more effectively, since we know that unexpected changes are not due to random variation. We begin by creating an input tensor using the Keras interface in TensorFlow to handle simple numeric features. This tensor is defined to have 4 elements, meaning each data sample is expected to contain 4 numeric values. Setting up this input tensor establishes the model's input layer, which is responsible for receiving and processing these 4 features. Giving it a clear name, such as numeric input, helps us keep track of its purpose within the overall model architecture. We begin by applying a dense layer from the Keras library to the input tensor to create a fully connected neural network layer. This layer is configured with 8 units, so it outputs a vector of length 8. We use the ReLU activation function, which introduces nonlinearity by turning negative values into 0, a common choice for hidden layers. The layer is given the name base dense for easier reference, and when applied to the input, it processes the data through its weights and activation to produce the transformed output used by later layers. We create a branch in the neural network to handle task A by applying a dense layer to the shared base features. This dense layer has 4 units and uses the ReLU activation function to add nonlinearity. We name it branch A dense to clearly mark its role. The base features from the previous layer flow into this dense layer, producing the specialized features used for task A. In this part of the model, we add a new fully connected layer with 4 units using the ReLU activation function, which keeps positive values and sets negative ones to 0. This layer is named to show that it processes features for task B. It takes the output from a previous base layer and transforms these features specifically for the second branch of the model. We add a skip connection by passing the input tensor through a dense layer with 4 units and a linear activation, which simply applies a linear transformation to the input. The output of this transformation is called the skip from input. This skip connection lets the original input features be carried directly to later parts of the model, helping information flow more easily and preserving important characteristics of the input. In this model, a Keras concatenate layer is used to merge 3 tensors into a single output. 2 branches called branch A and branch B each process the base features in different ways, while a skip connection passes the original input features directly to the merge point. By concatenating these 3 tensors, the model combines diverse feature representations into one richer tensor. This merged tensor can then be used for later layers, helping the model integrate multiple information pathways and learn more complex patterns. We add a shared dense layer to the model and apply it to the merged tensor from the previous branches. This layer has 6 units and uses the ReLU activation function. It is called the shared dense layer to emphasize that it processes features coming from all branches together. Its main role is to learn and refine patterns that are common across the different paths in the network. We define the output layer for the main prediction task using a dense layer with a single unit, so it produces one output value. It uses a sigmoid activation function, which is appropriate for binary classification because it outputs a value between 0 and 1. This output layer takes as input the shared tensor produced by the earlier layers in the network. We also assign it the name main output so it can be easily identified within the model. We add an output layer for an auxiliary prediction task using a fully connected dense layer with a single unit. This layer uses the sigmoid activation function, which is appropriate for binary classification because it produces outputs between 0 and 1. We name this layer aux output for clarity. It takes its input from branch B, so its predictions are based on the features computed in that branch. We are building a Keras functional model by defining its inputs and outputs. The input is a tensor that holds the numeric features. The model produces 2 outputs, a main output and an auxiliary output, which come from different branches in the network. This branching design lets the model handle multiple tasks at once. We also assign it the descriptive name, branch skip model, to reflect its structure and purpose. The summary function of the model is used to show a concise overview of its architecture, including the shapes of the layers and how they are connected. This helps you verify that the model's structure is correct. The line length is limited to 80 characters to keep the output easy to read, and nested layers are not expanded, so the summary stays compact and focused on the main structure. We use TensorFlow to create a small batch of dummy numeric data for testing. This data is a tensor filled with ones, arranged in 3 rows and 4 columns, and stored as 32-bit floating point values. It serves as stand-in input features, so we can check how the model behaves without needing real data. Before running the model, we first verify that the input data has the correct shape. In particular, we check that the second dimension of the sample data, which represents the number of features, is exactly 4. The model is designed to work only with inputs that have 4 features, so this check is essential. It helps catch any mismatch early and prevents errors when the model is executed. In this step, we run the model on a small sample batch to check its predictions. The input is a tensor filled with ones that has 3 rows and 4 columns, and the model is called with training turned off so it operates in inference mode rather than updating its weights. The model produces 2 sets of outputs, one for the main prediction and one for an auxiliary prediction, which we store separately. This process effectively tests the model's forward pass and shows how the sample input is transformed into outputs by the network. We print the shape of the input tensor to check how data moves through the model. This lets us verify that the input dimensions match what the model expects. Confirming these dimensions is essential for debugging and for understanding how the model is structured and how each layer processes the data. We print the shape of the main output tensor to check the dimensions of the model's predictions for the primary task. This quick check helps confirm that the output size matches what we expect. When the shape is correct, it indicates that the model's architecture is set up and functioning as intended. We print the shape of the auxiliary output tensor to check that its dimensions are correct. This lets us confirm that the auxiliary prediction task is producing outputs of the expected size. By verifying these dimensions, we ensure that this part of the model is wired correctly. In short, inspecting the tensor shape helps validate that the model's architecture is functioning as intended. This script shows how to use the Keras Functional API to build a neural network with branching and skip connections. It begins by setting the TensorFlow version and a random seed, then defines an input layer for numeric features, followed by a dense layer. The network splits into two branches with their own dense layers and also includes a direct skip connection from the input. And all three paths are concatenated and pass through a shared dense layer. From this shared representation, the model produces a main output and an auxiliary output taken from one branch. The script prints a summary of the model architecture, creates a small batch of dummy data, runs it through the network, and prints the shapes of the input and both outputs to illustrate how data moves through the model. Merging Add and Concatenate. When building models with multiple branches, an important design choice is how to merge the outputs, either by adding them or by concatenating them. Adding tensors combines information at corresponding positions, so all tensors must share the same shape. Concatenation instead joins tensors along a chosen dimension, increasing the size of the feature space and keeping each branch's features separate. This decision directly influences how information flows through the network and how you plan the shapes of intermediate tensors. Consider a model that processes an image with two filters, one capturing coarse shapes and the other capturing fine textures, each producing feature maps of the same size. By adding these maps together, the final output at each location and channel becomes the sum of the responses from both branches, forming a shared representation. This is especially useful in architectures with residual connections, where one path can refine or adjust another without changing the overall network design. However, because addition blends the signals, it becomes harder to tell which branch contributed which details. So this strategy works best when the branches provide complementary views of the same data. In practice, this encourages the network to distribute different feature responsibilities across the branches in a coordinated way. Concatenation is useful when you want to keep the outputs of different branches separate, so later layers can learn how to combine them. For example, one branch might process spending habits, another browsing interests, and another demographic data. And concatenation stacks all these features together without blending them too early. This creates a larger representation and higher computational cost, but it supports complex interactions such as in models that mix multi-scale features. In contrast, addition is better when you want a compact refinement of similar features, while concatenation is better for rich, diverse feature combinations. Python code, merging add, and concatenate. This script demonstrates how to use Keras functional merging operations by comparing the add and concatenate layers on simple network branches. The focus is on how these two merge types affect tensor shapes and how different branches are connected in the model. It does not address training performance, but instead highlights the structural differences between adding outputs and concatenating them. The script includes a comment that suggests installing TensorFlow version 2.20.0 if it is not already available in your environment. This is a precaution to make sure the required library is present so the code can run correctly. The comment shows a pip command that you can run in a shell to install TensorFlow. Because the line is commented out, it is optional and must be executed manually only when needed. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers module from Keras, which provides components like dense and convolutional layers. Together, these imports prepare the environment so we can define and work with neural network architectures. We use TensorFlow's random module to set a fixed seed so that any random operations produce the same results each time the code runs. This makes the sequence of random numbers deterministic. Doing this is especially important for debugging and testing because it lets us repeat experiments under identical conditions. As a result, our results become more reproducible and reliable. This command displays the version of TensorFlow currently in use. It provides a quick check that your environment is running the intended TensorFlow version. Confirming this helps ensure that your code is compatible with the installed library and behaves as expected. We begin by defining an input tensor in Keras that serves as the starting point for our model. This tensor is set up to handle dense features, so it expects a one-dimensional array with 4 values. Giving it a clear name, such as numeric input, makes it easier to recognize in the model's architecture. This input configuration is essential because it determines how data enters the model and is passed through the following layers for processing and transformation. We begin the first branch of the model with a dense layer from Keras that has 3 units, so it outputs a 3-dimensional vector. This layer uses the ReLU activation function to add nonlinearity and help the model learn more complex patterns. It is given a name for easy reference later, and it takes an input tensor with 4 features. Overall, this layer transforms the 4-dimensional input into a new 3-dimensional representation that can be used for further processing or combined with other branches in the model. We now build the second branch of our model, using a dense layer from Keras with 3 units and a ReLU activation function, and we give it a distinct name to tell it apart from other layers. This branch takes the same 4-dimensional input tensor as before, but processes it through a different transformation path. Setting it up this way allows us to later compare how different merging operations influence the outputs of the separate branches. We first check the shape of the output from the first branch to confirm its dimensions. Then repeat this for the second branch. This comparison verifies that both branches produce outputs with matching shapes. Ensuring identical output shapes is essential because the later merging steps depend on this compatibility to work correctly. In this model, 2 branches are merged using an element-wise add layer from Keras. Each branch ends in a dense layer, and the add operation combines their outputs by adding corresponding elements together. This produces a new tensor where each position holds the sum of the values from the same position in the 2 inputs. This approach is useful for combining features so that their joint contribution is emphasized in the final representation. In this model, we use a Keras concatenate layer to merge 2 network branches by joining their outputs along the last axis, effectively stacking their features together. This keeps all features from both branches in the combined output giving the model access to a richer set of information. The merged output is stored in a variable called concatenated, and the operation is given the name merge concat, so it can be easily identified in the model architecture. After merging the branches with the add layer, we print the shape of the resulting tensor to see how its dimensions look when values are combined element by element. We then print the shape of the tensor produced by the concatenate layer to observe how the dimensions change when features are stacked instead of added. Comparing these shapes helps clarify the structural difference between adding branches and concatenating them. We build a Keras model that takes a previously defined tensor as input and produces two merged outputs, one created by adding tensors and another created by concatenating them. These two outputs are specified together as a list when defining the model. This design lets the model generate both types of merged results from the same input data. We also assign the model a descriptive name, add versus concat model, so it is easy to identify when comparing how these two merging strategies affect the outputs. The summary function provides a concise overview of the model's architecture, listing each layer, its output shape, and the number of parameters. This helps you debug and confirm that the model is built as intended. The line length is limited to 80 characters, so the printed summary is easier to read. Nested models are not expanded in this view, which keeps the output more compact. We use TensorFlow's constant function to create a small batch of example numeric data made of two sets of 4 values. The first set contains the numbers 1, 2, 3, and 4. And the second set contains 4 copies of 0.5. We specify the data type as 32-bit floating point, so the values are compatible with TensorFlow's numerical operations. We run the model on a small batch of example data to generate outputs from both the element-wise addition branch and the feature concatenation branch. This step is essential because it produces concrete results from each merging method. By comparing these outputs, we can directly observe how element-wise addition and feature concatenation differently transform the same input data. To compare the effects of different merge strategies, we first inspect a small portion of the output from the add layer by taking the first element of its output tensor and converting it to a NumPy array for easier viewing. We then repeat this process for the concatenate layer, again focusing on the first element and converting it to a NumPy array. By examining these two slices side by side, we can directly compare both the values and the shapes of the outputs. This reveals how the add and concatenate layers transform and combine the data in different ways. The script ends by printing a message that compares the dimensions of the two merged outputs. It shows the shape of the tensor produced by element-wise addition and the shape of the tensor produced by concatenation. This highlights how each merging method changes the output size in a different way. As a result, it clearly illustrates how the choice between addition and concatenation affects the overall model architecture. This script shows how to merge two neural network branches in Keras using addition and concatenation. Each branch has the same dense layer, so they start with identical output shapes. When the branches are merged by addition, the resulting layer keeps the same shape as the original branches. When they are merged by concatenation, the feature dimension is doubled. Running example data through the model and viewing the summary makes it clear that addition preserves dimensionality, while concatenation expands it. Designing skip connections. When designing skip connections with the functional API, you should be clear about which layers you want to bypass and why. In deep models for images, audio, or long text, some layers compress or change the data so much that important details and stable gradients can be lost. Skip connections send earlier representations directly to later layers in parallel with the main path, so the model can combine raw and heavily transformed information. The functional API supports this naturally by treating tensors as nodes in a graph, which allows flexible data flow instead of a strict layer-by-layer sequence. When creating a skip connection, focus on what part of the network you are bypassing, where the skipped signal will rejoin the main path, and how the two streams will be combined. In image models, you must ensure that the tensor shapes match at the merge point, which may require transformations such as convolutions to align dimensions. In text models, you might route an early embedding layer directly to a later layer to preserve original sequence information. Using a functional style of model definition lets you explicitly pass earlier outputs into later operations, making skip connections a clear and intentional part of the model's design. Skip connections extend simple residual links into richer multi-scale architectures that work well in real-world tasks. In medical image segmentation, they reconnect early high-resolution features to later layers to recover fine details. In audio processing, they pass low-level features directly to the classifier to preserve subtle frequency patterns. For tabular data, they let raw inputs bypass dense layers and rejoin near the output, combining simple and complex feature interactions. The graph-based functional API makes it straightforward to design and test these different skip connection patterns and study their effects on performance and interpretability. Python code, designing skip connections. This script demonstrates how to use the Keras Functional API to create skip connections in a simple residual-style model. It builds the model, then inspects it to show how tensors flow through the network. The main goal is to understand the tensor shapes at each stage and how the graph-like wiring of layers implements the skip connections. The line with the exclamation mark is a shell command that installs TensorFlow version 2.20.0, which helps ensure compatibility and reproducibility by using a specific library version. In the script, this line is commented out, so it serves as a suggestion or reminder rather than something that runs automatically. If you actually need to install that version, you would remove the comment so the command can be executed. We start by importing TensorFlow, a library used to build and train machine learning models. From TensorFlow, we then use Keras, which offers a simpler, high-level way to create neural networks. Finally, we bring in the Keras layers module so we can add different kinds of layers, such as convolutional and dense layers, and use them to define the structure of our neural network model. We begin by importing tools for random number generation, so we can control their behavior. By setting the seed from both the numerical library and Python's built-in random module to the same value, we make sure they produce the same random values every time the code runs. We then set TensorFlow's random seed to that same value so its internal randomness is also consistent. Using these matching seeds makes our experiments reproducible, which is important for debugging and testing. We begin by printing the version of TensorFlow currently in use. Knowing the exact version helps us check compatibility with our code and libraries. It also makes debugging easier, since different versions can change features or behavior. This simple step ensures we understand the environment before moving on. We define the input shape of our model as 28 by 28 by 1, which means each input is a grayscale image that is 28 pixels high, 28 pixels wide, and has a single color channel. This size matches common machine learning image datasets, such as handwritten digit images. By specifying this input shape, we configure the model's input layer so it can correctly receive and process these images. We begin by defining an input tensor for our functional model in Keras, which serves as the model's entry point and specifies the shape of the incoming data. In this case, the input shape is 28 by 28 by 1, matching the format of grayscale images such as those in the MNIST dataset. Giving this input a clear name, like image input, makes it easier to identify and work with inside the model's architecture. We begin by passing the input image through a convolutional layer that uses 16 small 3x3 filters, with padding set so that the output keeps the same height and width as the input. This layer scans across the image and produces a set of feature maps. A ReLU activation function is then applied to introduce nonlinearity. Together, these steps transform the raw image into feature maps that highlight important patterns and edges. Here, the tensor produced by the first convolutional layer is saved in a separate variable, often called the skip tensor. This value is kept, so it can be added back into the network at a later layer through a skip connection. Such skip connections combine earlier and later outputs, which helps reduce problems like vanishing gradients and makes it easier for the model to learn identity mappings when needed. We now add a second convolutional layer to the tensor, using 16 small 3x3 filters with padding that keeps the height and width the same. This layer applies a ReLU activation function to introduce nonlinearity. By doing this, the network can extract deeper and more complex features from the input, improving its ability to learn intricate patterns in the data. Before adding a skip connection, the code first checks that the skip tensor and the main tensor have the same shape. This is important because adding tensors with different shapes would cause an error. If their shapes do not match, the program raises a value error stating that both tensors must share the same shape. This safeguard ensures that element-wise addition works correctly and helps maintain the integrity of the model's architecture. Here we combine two tensors using element-wise addition. One tensor, called the skip tensor, carries features from an earlier layer, while the other comes from the main path of the network. Adding them together merges information from both paths and helps the model learn by preserving important features from the skip connection. This is done with the Keras add layer, which performs the addition and keeps the output in the correct shape for the following layers. After merging the skip connection with the main path, the network applies a max pooling layer to the combined output. This layer scans the feature map using small 2x2 windows and keeps only the maximum value in each window. As a result, it reduces the spatial dimensions of the data, effectively downsampling the feature map. This makes the representation more compact and emphasizes the most prominent features for later processing in the network. The model takes the current tensor, which holds the processed image data, and flattens it into a one-dimensional feature vector. This step is essential because the following dense layer needs a flat input to perform classification. By collapsing the spatial dimensions into a single line of values, the model converts the image features into a format that can be interpreted and processed by the dense layer. We add a dense, fully connected layer with 10 units to serve as the model's classification layer. It produces a probability distribution over 10 classes, meaning each output value represents the probability of a specific class. This layer uses the softmax activation function so that all outputs are between 0 and 1 and together add up to 1. We name this layer class output to clearly indicate its role in providing the final class probabilities. We are building a functional model in Keras by defining its input and output tensors. The input is the image data tensor created earlier, and the output is the final dense layer that produces class probabilities. We assign the model a name, skip demo model, so it can be easily identified later. This approach wraps the entire neural network, including its skip connections, into a single structure that can be trained and evaluated as one complete model. The model's summary function is used to print a compact description of the network's architecture, listing each layer along with its output shape and number of parameters. The summary is formatted to keep the lines a manageable length and does not expand nested layers, so the display stays focused on the main structure. Reviewing this summary is an important step to confirm that all layers are connected properly and that the output shapes match what you expect. To test the model, we generate a small batch of random images. We create an array with 4 images, each 28 by 28 pixels with a single channel. The values in this array are random numbers produced by a numerical library. We set the data type to 32-bit floating point so it matches the model's expected input format. In this step, the model performs a forward pass on a sample batch of images, meaning it processes the inputs through the network to generate predictions. The model is in inference mode, so it only computes outputs without updating any weights. This check is important to confirm that the model runs correctly and that its outputs have the expected shape, indicating the architecture is set up properly. We inspect tensor shapes at key points in the model to verify that data flows correctly through the network. First, we check the shape of the input batch to confirm the dimensions entering the model. Then, we examine the shape of the skip tensor from the first convolutional layer, followed by the shape of the merged tensor created when this skip tensor is added to the output of the second convolutional layer. Finally, we confirm the shape of the output batch after the forward pass to ensure the model produces results with the expected dimensions and that the skip connection is integrated properly. This script builds a simple residual neural network in Keras to process single-channel grayscale images. It uses convolutional layers to extract features and includes a skip connection that adds the output of the first convolution directly to the second when their shapes match, helping preserve information and reduce vanishing gradients. After the skip connection, the model applies pooling, flattens the features, and passes them through a dense layer to classify images into 10 categories. The script also sets up a deterministic environment for reproducible results, prints a summary of the model architecture, and verifies that the input and output shapes behave as expected. Overall, it serves as a basic example of how skip connections can be implemented to improve neural network performance. Inspecting functional models. Reading model summaries. When using the Functional API, the model summary is essential for understanding how your model is built. It shows the computational graph, including how data flows from each input through the layers to the outputs. By checking the order of layers, their names, and the shapes of the tensors, you can see how different branches, such as image and tabular inputs, are processed and where they merge. Reviewing this summary helps you confirm that the architecture matches your design and avoids unintended configuration errors. Understanding tensor shapes in a model summary helps you track how data changes as it moves through the network. Each layer's output shape shows how inputs, such as a sequence of words, are transformed into higher-level representations and eventually into a compact vector for tasks like classification. If you see unexpected changes in dimensions, it signals that you should verify whether those transformations are intended. With experience, you develop an intuition for typical shape progressions in architectures like convolutional and encoder-decoder models, which makes it easier to spot inconsistencies. In functional models, it is important to understand how layers connect, especially when there are branches, merges, or skip connections. The model summary helps you spot layers that take multiple inputs or send outputs to several other layers, so layer names and indices become key to tracking these links. By carefully checking layer names, output shapes, and connection patterns, such as where an early image feature map feeds directly into a later fusion layer in a medical diagnosis model, you can verify that all skip connections and merges are correctly defined. This reduces the chance of hidden architectural bugs that could harm model performance or training stability. Python code, reading model summaries. This script demonstrates how to read and interpret model summaries using a small example built with the Functional API. Its main goal is to help you understand how to read the reported layer shapes and how different layers are connected. As you follow the summary, pay attention to how data flows through the model and how each layer transforms the input. This will help you better understand the structure and behavior of neural network models. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Specifying this exact version makes sure the code uses the expected features and behaves consistently. This practice helps avoid problems that can occur when newer library versions introduce changes that might break existing code. We start by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layers module from Keras, which provides the key components, such as convolutional and dense layers, that we use to construct the different parts of our neural network. This line displays the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility with other tools and libraries. It is also useful for debugging, because different TensorFlow versions can change features or behavior. By printing the version, you can quickly confirm that your environment matches the requirements of your project. We set the random seed in TensorFlow to a fixed value, such as 7, so that any random operations produce the same results every time the code runs. This makes our experiments reproducible, meaning we can reliably repeat them and get consistent outcomes. Reproducibility is especially important when debugging issues or comparing how different models perform under the same conditions. We define an image input layer in Keras that accepts 8 by 8 pixel images with a single color channel, which is typical for grayscale data. We assign this layer a clear name, image input, so it can be easily identified later in the model. This input setup is essential because it specifies the exact shape of the image data the neural network will receive. With this defined input, the network can properly process and learn from the features in the images. In this step, we define a tabular input for a Keras model that will handle structured data. The input is set up as a one-dimensional array with 4 elements, meaning it expects 4 features. We also assign it the name tabular input, so it can be easily referenced within the model. This configuration allows the model to process tabular data alongside other inputs, such as images, in a multi-input neural network. We begin by building a small convolutional block to process image data using a 2-dimensional convolutional layer from Keras. This layer applies 4 filters, each with a 3 by 3 size across the input image. It uses the ReLU activation function to introduce nonlinearity. The result is a set of feature maps that represent important visual patterns and will be passed on to later layers in the model. This step takes the output from the previous convolutional layer and flattens it into a one-dimensional vector. Flattening is important because it converts the multi-dimensional image features into a format that dense, fully connected layers can accept. In other words, it unrolls the feature matrix into a single line of data so it becomes compatible with the following layers. It is called image flatten to clearly describe its role in the model's architecture. Here we define a dense or fully connected neural network layer in Keras with 8 output units, so it produces an output vector of length 8. We use the ReLU activation function to add nonlinearity, which allows the model to learn more complex patterns. The layer is given the name tabular dense, so it can be easily identified later in the model. It takes the tabular input as its input, meaning it processes data coming from the tabular branch of the network. Here, we create a skip connection for the tabular data branch using a dense layer with 8 units and a ReLU activation. This layer processes the tabular input to extract additional features. Later, These features are combined with the main tabular path. The skip connection helps preserve important information and improves the model's ability to learn more complex patterns. In this step, we combine two sets of features from the tabular data branch. The main features are first processed through a dense layer, and then merged with the skip connection features using a concatenate layer from Keras. This operation joins the transformed features with the original ones into a single representation. By doing so, the model can use both the processed and raw information, which helps it learn more complex patterns from the tabular data. In this part of the model, we combine the outputs from two branches, one that processes image data and another that processes tabular data. We use a concatenation layer from Keras to merge these outputs into a single tensor. This step is important because it lets the model integrate features from both data types. After this merge, the combined tensor can be passed on for further processing and used to make more informed predictions. After merging the image and tabular data branches, we pass the combined features into a hidden layer with 16 units. This layer uses the ReLU activation function to introduce nonlinearity, which helps the model capture more complex patterns. We call this layer the Fusion Dense layer to highlight its role in processing and refining the merged information from both data sources. This line defines the model's final layer as a dense layer with 3 units, where each unit represents one class in the classification task. It uses the softmax activation function, which is well suited for multi-class problems because it converts the raw outputs into probabilities that add up to 1. This final layer takes the processed information from the previous hidden layer and produces the model's overall prediction. In this step, we build a functional model in Keras by defining its inputs and outputs. The inputs come from the two branches we created earlier, one for image data and one for tabular data. The output is the final classification layer that produces the prediction. This structure lets the model process image and tabular information at the same time and merge their features to make a combined prediction. The code prints a summary of the model that gives a compact overview of its architecture. It lists the layers, their types, the shapes of their outputs, and how many parameters each one has. The summary is formatted to keep each line within about 80 characters, so it is easy to read. Nested models are not expanded, which keeps the summary concise and focused on the main structure. The code first reports the shapes of all the model's input layers by going through each input and reading its shape attribute, giving you a clear picture of the dimensions the model expects. It then reports the shape of the model's output layer, showing the dimensions of the data the model produces. Together, these checks help confirm that the model's architecture matches the intended input and output sizes. This script builds a simple neural network using TensorFlow's Functional API with 2 input branches, one for 8x8 grayscale images and one for tabular data with 4 features. The image branch applies a convolutional layer and then flattens the result, while the tabular branch passes through dense layers with a skip connection. These processed features are merged, passed to another dense layer, and then fed into a 3-class output layer for classification. The script also prints the TensorFlow version, sets a random seed for reproducibility, and displays a model summary so you can verify the architecture and how data flows through the network. Visualizing model graphs. When building models with a graph-based interface, seeing the network as a visual graph is far more helpful than reading only text descriptions. Each layer appears as a node, and the tensors are shown as directed edges, so you can easily follow how data moves from inputs through transformations to outputs. In a model that processes both images and text, the graph clearly shows the separate input branches, the sequence of layers in each branch, and the point where they merge. This makes it much easier to understand the overall architecture and the complexity of the connections. Graph visualizations are especially important for understanding complex neural network architectures with branching, merging, or skip connections. In models like residual networks, they show the main path and shortcut connections. And in multitask models, they reveal how a shared backbone splits into multiple output heads. By clearly displaying where branches split and rejoin, these diagrams help you verify that the structure is correct, with no unintended loops or missing connections. This reduces errors such as merging branches too early or forgetting to reconnect a skip path. Visual model graphs are very useful for debugging neural networks because they show the input and output shapes at each layer, so you can see how tensor dimensions change through the model. This makes it easy to check whether spatial dimensions shrink as expected, whether channels line up correctly when layers are merged, and whether the final vectors match what dense layers require. When there is a shape mismatch or an unexpected flattening, the graph view helps you pinpoint exactly where it occurs. By following the arrows and shakes, you can systematically find and fix issues and refine your model with more confidence. Python code, visualizing model graphs. This script demonstrates how to visualize a Keras functional model, emphasizing its graph structure and the shapes of the tensors that flow through it. The goal is to help you understand how different layers are connected and how data dimensions change across the network. To follow the explanation properly, run the cells in the given order so the visualizations and descriptions build on each other. The script includes an optional command to install TensorFlow version 2.20 in a Colab environment. Using this specific version helps keep the code compatible and results reproducible by relying on a consistent library version. The command is commented out so it doesn't run automatically. However, you can enable it when needed to match particular environment requirements. We begin by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we use Keras as a high-level interface that makes it easier to build neural networks. We also import the layers tools from Keras, which provide the basic components for creating the different parts of a neural network. Together, these imports give us everything we need to define and train our model. We begin by printing the TensorFlow version being used. This step is important for reproducibility because it lets anyone running the code confirm they are using the same TensorFlow setup. Different versions can change how the code behaves and the results it produces, so recording the version helps ensure consistent and comparable outcomes. We set a random seed in TensorFlow so that any operations involving randomness give the same results every time the code runs. Using a fixed seed value, such as 7, makes the model's initialization and any data shuffling repeatable. This consistency is important because it allows us to debug more easily and reliably compare model performance across different runs. We define an input layer in Keras to handle image-like data, specifically images that are 28 by 28 pixels with a single grayscale channel. This layer is named Image Input to clearly identify its role in the model. It serves as the entry point for the network and prepares the data so that the following convolutional layers can process the images effectively. We define a small convolutional block using Keras by applying a two-dimensional convolutional layer to the input image. This layer uses 8 filters of size 3 by 3 that scan across the image. It applies the ReLU activation function to introduce nonlinearity. Together, these operations help the model learn spatial patterns in the image, such as basic features like edges and textures. We now apply a max pooling layer to the output of the previous convolutional layer. This layer scans the feature map in small 2 by 2 regions and keeps only the largest value from each region. As a result, the spatial dimensions of the feature map are reduced. This downsampling lowers computational cost and helps the model concentrate on the most important features in the data. Here we add another convolutional layer to the model to increase the depth of its feature maps. This layer uses 16 small 3x3 filters and applies the ReLU activation function. By stacking this layer on top of the previous ones, the model can build on earlier features and capture more complex patterns in the data. The model takes the output from the previous convolutional layer and flattens it into a one-dimensional array so it can be passed into dense layers. Dense layers expect input in a flat format, not as a multi-dimensional tensor. By flattening the features, we convert the spatial feature maps into a single vector. This prepares the data for further processing and allows the dense layers to learn from all the combined features effectively. We add a second input branch to handle numeric metadata alongside the image data. Using Keras, we create an input layer that expects a one-dimensional array with 4 numeric values. We also assign this input a clear name, so it can be easily referenced within the model. This design lets the network learn from both the image information and the additional numeric data at the same time. We process the metadata by passing it through a dense layer with 8 units that uses a ReLU activation function. This nonlinear layer helps the model capture more complex patterns in the metadata. The output of this step is a transformed representation of the original metadata, called meta features. These meta features are then used later in the model for further learning and prediction. In this step, we combine features from 2 sources, the image data and its associated metadata. Using a concatenate layer in Keras, we merge the flattened image features with the processed metadata features into one tensor. By joining them into a single representation, the model can learn from both visual and numerical information at the same time. This combined input is especially useful for tasks that depend on understanding both types of data together. After merging the features from the image and metadata inputs, we pass them through a dense layer with 16 units that uses the ReLU activation function. This activation introduces nonlinearity, allowing the model to capture more complex relationships in the combined data. By processing the integrated features in this way, the model is better able to learn useful patterns and improve its prediction accuracy. We now define the output layer of the model, which performs binary classification. It is a dense layer with a single neuron, so it produces one output value. This neuron uses the sigmoid activation function, which maps the output to a value between 0 and 1. That value represents the predicted probability of the positive class. Applying this layer to the previous hidden layer completes the model's architecture. In this step, we build a functional model in Keras by specifying its inputs and outputs. The inputs are 2 streams of data, one for images and one for metadata, both defined earlier in the script. The output is the final prediction layer of the network. This design lets the model process image data and additional numeric information at the same time and combine them to make a binary classification decision. It is especially useful when you need a single model that integrates multiple types of input data. Calling the summary method on the model gives a concise overview of its architecture. It lists each layer's name, type, and output shape, so you can confirm the structure and check that data flows correctly through the network. The line length is set to 80 characters to keep the printed summary readable. The expand nested option is turned off, so nested models are not expanded, and the summary stays focused on the top-level structure. We use Keras tools to create a visual diagram of the model's architecture and save it as a PNG file called functional model. This diagram shows the shapes of the tensors as they move through each layer, which helps us understand how the data is transformed at every step. We choose not to display data types, so the focus stays on the structure and tensor shapes. Layer names are included to make the diagram clearer and to show how the model is organized and how information flows through it. The code uses the operating system module to check whether a plot file named functionalmodel.png exists in the current directory. It calls a function that returns true or false, depending on whether the file is present. Based on this result, it prints a message to the console indicating if the plot file was successfully created. This provides a simple confirmation that the file generation step worked as intended. This script shows how to visualize the architecture of a Keras functional model, emphasizing its graph structure and tensor shapes. It builds a model with two inputs, one for image data processed through convolution, pooling, and flattening, and another for numeric metadata processed through a dense layer. These two feature streams are merged, passed through additional dense layers, and used to produce a binary classification output. The script prints a summary of the model to display layer shapes, saves a visual diagram of the model as a PNG file, and confirms that this plot was created, helping users understand the model's structure and data flow for debugging and optimization. Debugging shape mismatches. When building models with layered graphs, a frequent problem is shape mismatch, where the dimensions of input tensors do not match what each layer expects. These issues usually appear as incompatible shape errors, so it helps to trace a single example through the model and check the batch, spatial, and feature dimensions at every step. For example, when combining image data with tabular features, you must flatten the image data before concatenating it with the other features to avoid mismatches. By clearly planning and verifying the intended shape at each stage, you can quickly locate where unexpected dimensional changes occur and focus your debugging on that part of the model. To fix shape mismatches in your model, compare the expected tensor shapes with the actual ones using tools that reveal intermediate dimensions. When an error appears at a merge or addition layer, trace the input and output shapes of the surrounding layers to find where they diverge. For skip connections, make sure both tensors match in height, width, and channels, and if pooling or convolution changes these, insert an extra layer to adjust the earlier tensor. The same idea applies in sequence models, where consistent reshaping or pooling is needed so sequence length and feature dimensions line up correctly. When you run into shape mismatches in a model, build habits that help you diagnose them systematically. Clearly state what each tensor represents, such as a batch of audio clips with certain time steps and features, or a set of scalar predictions. If a layer receives a tensor with unexpected dimensions, treat it as a sign that you misunderstood how the previous layer transforms shapes, for example, by forgetting to flatten a convolutional output. Testing the model with small synthetic data can help you locate exactly where things go wrong. With practice, you will develop an intuitive sense for how each layer changes tensor shapes, and shape mismatches will become straightforward to fix. Python code. Debugging shape mismatches. This script demonstrates how to debug shape mismatches when working with tensors in the Keras Functional API. It focuses on checking the shapes of tensors at different points in the model and identifying where they do not align as expected. By carefully inspecting these shapes, you can find and fix errors that would otherwise cause the model to fail. The main goal is to help you understand and resolve shape-related issues in your neural network architecture. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Specifying this exact version makes sure the code uses the expected library and helps prevent compatibility problems that can occur with different versions. This practice keeps the software environment consistent across different systems and runs. We begin by importing TensorFlow. a library used to build and train machine learning models, and Keras, its high-level interface that makes creating neural networks easier. From Keras, we also import the Layers module, which provides components like convolutional and dense layers. Together, these imports give us the essential tools needed to define and work with neural network architectures in our script. We start by importing a numerical library to handle calculations, then set a random seed so that any random numbers it generates are the same each time the program runs. We also set a random seed for the deep learning framework to control its internal randomness. Using these seeds makes the code run in a deterministic way, which is important for reproducibility. This consistency helps with debugging and allows us to reliably compare results across different runs of the code. We begin by printing the current TensorFlow version to confirm which one is being used. This helps us check compatibility and know which features and bug fixes are available. Seeing the version makes it easy to verify that the environment matches what we expect. This is important for debugging issues and for reliably reproducing results. We begin by defining an input tensor for an image in Keras, shaped as 28 by 28 pixels with one color channel, which matches a typical grayscale image. We also assign it a clear name so it can be easily identified within the model. This input setup is essential because it specifies how image data will be fed into the neural network, enabling the model to process and learn from the images correctly. We begin by passing the input image through a convolutional layer that uses 8 small 3x3 filters with a ReLU activation and padding that keeps the output the same height and width as the input. This step extracts useful features from the image while preserving its spatial size. We then apply a max pooling layer with a 2x2 window, which cuts the height and width of the feature map in half. This downsampling reduces computation while keeping the most important features. In this step, we build a skip connection by passing the image input through a 1x1 convolutional layer with 8 filters and a ReLU activation. This layer changes the input into a new representation that has the same number of channels as the main branch, while keeping the height and width the same. The design is intentional so that a shape mismatch will occur later in the script, emphasizing why neural network operations like addition require compatible shapes. We first print the shape of the main branch tensor, which comes from applying convolution and pooling to the input image, so we can see the data dimensions at that stage of the network. We then print the shape of the skip branch tensor, which is produced by a different convolution applied directly to the same input image. Comparing these two shapes lets us verify that the branches are compatible before performing operations that require matching dimensions, such as adding the tensors together. This code prints a message to warn you about a possible problem when adding two tensors. It reminds you that tensor addition only works correctly when the tensors have the same shape. In other words, their dimensions must match. Checking this before performing the operation helps you avoid runtime errors in tensor computations. To fix the shape mismatch between the skip path and the main branch, we add a max pooling layer to the skip path. This layer reduces the spatial size of the skip tensor by pooling over small 2x2 regions. As a result, the skip path output is resized to match the main branch. With matching shapes, the two paths can be added together without causing errors. We now check that the tensor shapes match so we can safely add them. To do this, we look at the shape of the fixed skip tensor and confirm it has been correctly downsampled. This verification tells us that its dimensions are aligned with those of the main branch. Once the shapes are compatible, we can perform the addition without running into shape mismatch errors. In this step, We add two tensors that have the same shape, using the add layer from Keras to perform element-wise addition. This works because both tensors have been adjusted to be compatible in size, so each element in one tensor lines up with a corresponding element in the other. Ensuring matching shapes is essential to keep the model's architecture consistent and to prevent runtime errors caused by shape mismatches during the addition operation. We first flatten the tensor from the previous layers into a one-dimensional array so it can be used by the dense layer, which expects a flat input. This flattened data is then passed into a dense layer with 10 units that uses a softmax activation function. This final layer serves as the output of the model and produces a probability distribution over 10 possible classes.
Such a setup is commonly used for classification tasks, like recognizing digits.
In the Keras Functional API, we build a model by connecting an input tensor to an output tensor. In this case, the input is the image tensor defined earlier, and the output is the final dense layer that generates the class predictions. We also assign the model a name, such as debug model, so it can be easily identified later. This setup defines a neural network where data flows from the input through a sequence of layers to produce the final output. Calling the model's summary function gives a concise overview of its architecture, including the layers, their output shapes, and the number of parameters. Keeping nested layers collapsed focuses the summary on the high-level structure instead of internal details. Enabling the option to show which parts are trainable highlights the layers whose parameters will be updated during learning. Overall, this summary is a quick way to confirm that the model is organized correctly and that the shapes are consistent throughout the network. We create a small batch of synthetic image data using a random number generator, producing 4 grayscale images. Each image is 28 by 28 pixels with a single channel, which mimics simple image inputs. The data type is set to 32-bit floating point values to match TensorFlow's expected format and support efficient computation during later processing. The code performs a forward pass through the model using the sample images, meaning it processes the inputs to produce predictions. The model is explicitly set to inference mode rather than training mode so that components like dropout behave correctly for prediction. The resulting outputs for the batch of images are stored as the model's predictions. The code prints the shape of the prediction batch to check that the model's output has the correct dimensions. This confirms that the predictions match the expected format. Verifying the output shape helps ensure the model is processing the input data properly and producing results in the desired structure. This script shows how to debug and fix shape mismatches in a neural network built with the Keras Functional API. It creates a simple convolutional model with a main path and a skip connection, then demonstrates that adding these paths fails when their tensor shapes do not match. By printing the shapes, it identifies the mismatch and then corrects it by downsampling the skip path with max pooling so both branches align. After that, the model adds the tensors, flattens the result, and applies a dense layer for classification. Finally, it summarizes the model and runs synthetic image data through it to confirm that the network architecture works and produces predictions with the expected shape. In this lecture, you learned to define Keras models using the Functional API with explicit input and output tensors, implement models with branching or skip connections using the Functional API graph structure, and visualize and debug functional models to ensure correct tensor shapes and connections. In the next module, Module 4, we will go over training workflows. Thank you for your attention. See you all in the next lecture.